Hello students, welcome back to my channel. In this video, we will study about the kinetics of copolymerization technique. Okay, we know that copolymer means or copolymerization means there must be at least two monomers, right? There must be the presence of two monomer. I call the monomer as M1 and M2. Okay, these are the two monomers. Okay, and these two monomers undergo polymerization by free radical polymerization technique. Okay, we already studied about the free radical polymerization technique. Now here we are considering two monomer, they are undergoing polymerization by free radical polymerization technique. Okay, we know that in the free radical polymerization there must be presence of initiator, right? So there is a presence of initiator and this initiator will cleave homolytically to give the free radicals, right? This is what we studied in free radical polymerization technique. Okay, I call initiator as R or simply R2. Okay, so this is my initiator. Okay, this is the initiator. Now what happens? This will cleave homolytically. Okay, that means one of the electron goes with this R and this the electron is also going on the another R. So you will get two free radicals. Okay, this is free radical that is generated from what? From the homolytic cleavage of initiator. Okay, now we have two monomers M1 and M2, right? So in the initiation step, okay, the first step is the initiation. So in the initiation step, the free radical, okay, one of the free radical that is generated here, that will attack M1. Okay, there are two monomers. So what happened? M1 free radical, that means the free radical over here is shifted to M1 free radical. Similarly, the another free radical, okay, in this one, okay, this free radical attacks the another monomer M2 to form RM2 free radical. Okay, the free radical here shift over here. Okay, this is what happens in the initiation step. Okay, I call this as equation number 1, this is 2, this is 3. Okay, the next step we have is the propagation step. Okay, the propagation step. So in the propagation step, what happens? The propagation step, the free radical generated here, okay, the free radical generated here will attack the more monomer so that the chain length keep increasing, right? So that is what happening in a propagation. So M1 free radical, okay, that will attack the monomers. There are two monomers M1 and M2. So first I consider it is attacking M1. Okay, next I consider the same free radical is attacking the another monomer M2. Okay, because we have two monomers, right, M1 and M2 in the reaction mixture. There are two monomers, so this free radical can attack this or this. Okay, now suppose if it is attacking M1, what happen? The free radical over here will shift over here, right? M1 free radical, correct? Similarly, here also happens the same. The free radical over here will shift here. M1 M2 free radical. Okay, so far we consider only this monomer, free radical, correct? Similarly, we have this free radical also, right? So M2 free radical, this can now attack either M1 or it can also attack M2 also. Okay, so here what happens? M2 M1 free radical, right? Because free radical here shift over here. Similarly, here M2 free radical. Okay, so I continue the number. This is 3. So this is 4, 5, 6 and this is 7th equation. Okay, now I call the rate constant. The rate constant for this step, okay, for the first one as Ka. Okay, let K be for this and Kc and similarly Kd for the last equation. Okay, where Ka, Kb, Kc, Kd are what? Rate constant. Okay, the rate constant of equation 4, 5, 6, 7 respectively. Okay. Okay. Now what we do is we will write the rate of all these 4 equations. Okay. Next step is what? The rate. The rate of 4 propagation step. The rate of 4 propagation step. Okay. There are 4 propagation steps. Okay. That is 4, 5, 6, 7. These are the propagation steps. So now what we are doing, we are writing the rate of that. Okay. So here the rate is given by, for this RA, for this RB, RC, and this is RD. Okay. So what is RA? RA is what? RA is given by rate constant, that is Ka, into concentration of reactant. So here reactants are RM1 free radical and M1, right? So concentration of this and concentration of this. Now here you can consider only this one. You can or you need not write RM1 free radical. Okay, you can write, but it creates complexity in the final equation. That is why I am only writing M1 free radical and M1. Okay, so M1 free radical is this and this, because free radical present on M1 is shifted over this M1, right? That is why I am considering only that one. Okay, this is my equation number 8. Okay, similarly write RB, RC and RD. Okay, these are the 4 rate equations we have. Okay, now what is RB? Look into the equation number 5 and write Kb into concentration of what? M1 free radical and M2. Okay, you need to consider which is free radical from where to where that is migrating. Okay, the free radical is present over this M1, right? So M1 free radical means the free radical from here is shifting to here. That is why I am considering only this. Okay, you can consider this one also, but it look little complex. Okay, 9. Similarly, RC means what? Kc into concentration of M2 free radical and M1. Okay, then you have RD, Kd into concentration of M2 free radical and concentration of M2. This is my equation number 10. This is my equation number 11th. Okay, these are what? The rate equations. Okay, the rate of 4 propagation steps that we have considered. Okay, now we will now here the basic assumption is that the assumption is that the reactivity, the basic assumption is that the reactivity, the basic assumption is that the reactivity of any growing chain, the basic assumption is that the reactivity of any growing chain depends only on the end monomer unit, carrying free radical site. Okay, and not on the number of types of monomer that is already present in it. Okay, already present in it. So what's the meaning? So basic assumption is that the reactivity of any chain, okay, any growing chain only on the end monomer unit that is carrying free radical. Okay, so here according to this, whatever the other monomer that is present in the chain, it doesn't depend on that. It only depend upon which monomer is there carrying free radical at the end of grooving polymer chain. Okay, this is what the basic assumption is. Okay, basic assumption is that the reactivity of any grooving chain depends upon end end monomer unit that is carrying the free radical side, not on the molecule that is present in the interior of that chain. Okay, so according to this basic assumption, we say that the rate at which the monomer M1 and M2 are consumed during the course of reaction, which reaction? Propagation reaction, can be expressed as okay, what's the meaning? The rate at which the monomer M1 and M2 are consumed during the course of the reaction can be represented as. Now let us consider if the monomer M1 is consumed, then it is represented by, rate is represented by what? D by dt minus D by dt of concentration of M1. Okay, what is this represent? That will represent the rate at which the monomer M1 is consumed. So it is equal to what? So you need to look into the propagation reaction. So you need to see where M1 is consumed. So this is going back to the propagation. Okay, so where M1 is consumed? In this step M1 is there. In this step M1 is consumed, correct? That is in the equation number 4 and 6, the M1 is consumed. Now rate corresponding to that is what? Equation number 8 and equation number 10. So these are the rate corresponding to the reaction where M1 is consumed, correct? So we are considering RA plus RC. Okay, hope you are getting to know here. Why you are considering RA and RC? Because in these two reactions, M1 monomer is consumed. So now write what is RA. From the equation number 8, we have RA means what? Ka into concentration of M1 free radical, concentration of M1. Okay, plus RC. RC means from the equation number 10. Okay, Kc M2 free radical and concentration of M1. Okay, this is what you have. Now this is equation number what? 12. Okay, this is equation number 12. Now similarly consider the rate at which M2 is consumed. So which are the two rate become equal? So you need to look into the reaction where M2 is consumed. So here and here, that is in the equation number 5 and 7, M2 is consumed. Now see the rate at rate corresponding to these two equations, that is 9 and 11. That means you need to add them. You will get the rate at which M2 is consumed. So you can write RB and RD. Okay. Then write what is there under RB. That is KB, M1 free radical M2, concentration of M2, and plus KD, concentration of M2 free radical, concentration of M2. Okay. This is my equation number 13. Okay. Next, at steady state, okay, at steady state or at equilibrium. Okay, at equilibrium what happens? The rate of disappearance of particular chain is equal to rate of formation of particular chain. Okay, so at steady state what happens? The rate of disappearance of particular chain is equal to what? The rate of formation of particular chain. Okay, so this is at equilibrium. The rate of disappearance of particular chain must be equal to rate of formation of particular chain. So according to this statement, which are the two rate become equal? Can you say? Here you need to look here, the rate equation that you have written here. Okay, that is 8, 9, 10, 11. Okay, these are the four rate equations. Now see here, in the first equation, which is the free radical present? M1 free radical is present, correct? M1 free radical. Now if you come here, what is the free radical? Once again M1 free radical. It didn't change, right? It is M1 free radical. Okay. Okay. Now from here to here M1 free radical, but once you move down, you will get M2 free radical, right? So once again next equation also contain M2 free radical. Now can you tell? The rate of disappearance of particular chain is equal to rate of formation of particular chain. Means which free radical disappeared? Sorry, the which free radical is disappeared? Okay, initially M1 free radical was there. Next also it is the same, but now here it disappeared and formed a different free radical, right? So this is the rate you need to consider at which the particular chain disappeared, and this is the rate at which the particular chain is formed, correct? So you need to consider RB equal to RC. Okay, hope you are understanding. So here also M1 free radical, here also M1 free radical, but once you come down, this is disappeared, this is formed, correct? So that is why at the steady state RB become equal to RC. Okay, now write what is there under RB. RB is what? Kb. Okay, I am writing the same equation here. M1 free radical concentration of M2 is equal to Kc M2 free radical concentration of M1. Okay, now from this equation is 14, right? 13, and this is equation number 14. Okay, the next from this equation what I do is I write M1 free radical divided by M2 free radical. Okay, from which equation? From the above equation itself I am writing this. Okay, now what happens? You are keeping M1 free radical here, M2 free radical is taken below here. So you have Kc into concentration of M1 and bring this and this below here. Okay, Kb into concentration of M2, and this equation is what? Our equation number 15. Okay, this is 14, this is 15. Okay, next, relative change in the monomer concentration is given by what? Relative change, right? Relative change in monomer concentration is given by, okay, the relative change in the monomer concentration is given by, what you need to do is you need to divide equation 12 by equation 13. Okay, where is our equation 12? See, and divide that by equation number 13. So here we have equation number 12, this is equation number 13. So what I do is I write equation 12, left hand side is dm1 into d concentration of m2. Okay, why? Because minus minus, if you divide, no, what happened? Minus minus get cancelled, dt get cancelled, so you left with d into concentration of m1 divided by d into concentration of m2. So remaining term I write as it is. Okay, Ka m1 free radical concentration of m1 plus Kc concentration of m2 free radical concentration of m1 whole divided by what? 13 equation, that is Kb m1 free radical m2 plus Kd concentration of m2 free radical concentration of m2. Okay, this is your equation number what? 16, right? Yes, this is your equation number 16. Now substitute 14 in the equation number 16. Okay, substitute 14. Okay, see what is there in the equation number 14. Okay, you have 14 here. what you need to do? Substitute 14 in 16. Okay, so where you need to substitute? So in the this is 14, this is 16. Okay, so in the numerator you have Kc, M2 free radical, M1. So in this place I am writing this, and in the denominator, in this place I am writing this. Okay, substituting, you get D into concentration of M1 divided by D into concentration of M2 is equal to Kb into M1 free radical M1 plus, in this place what I am doing, I am substituting this Kb into concentration. I made a mistake, I guess. This is not Kb, correct, this is Ka. Okay, see, make a correction, it is Ka. Okay, so Kb into M1 free radical M2 divided by, so in this place what I am doing, I am substituting this from the equation number 14. M2 free radical M1 plus Kd into Kd into concentration of M2 free radical concentration of M2. Okay, now I call this equation number as 17. Okay, or 17. This is equation number 17. So in the numerator, if you see M1 free radical is there. I take it outside as the common term. Even in the denominator, you have M2 free radical common. So keeping it outside and writing the remaining term as such. Okay. So you will get Ka into concentration of M1 plus Kb into concentration of M2 divided by Kc into concentration of M1 plus Kd into concentration of M2. Okay, this is what you get. Now what you do is, here you have M1 free radical and M2 free radical, no? So in the above equation, substitute 15, okay? Sorry for the disturbance, okay? You need to substitute 15 in this equation. So see what is your 15th equation. So here I have 15th equation. So M1 free radical divided by M2 free radical is this, right? So I am substituting this in the place of here. Okay. So I get what? D M1 D concentration of M2. You get what? Kc concentration of M1 Kb concentration of M2. Okay, this is what you get. And write the remaining term as such. Okay, what you have? Ka concentration of M1 plus Kb into concentration of M2 and Kc into concentration of M1 and Kd into concentration of M2. Okay, this is what you have. Well, now what you need to do is, to the numerator multiply and divide by Kb. Okay, to the numerator what you need to do, multiply and divide by Kb. Okay, to the denominator multiply and divide by Kc. Okay, for the denominator what you need to do, multiply and divide by Kc. Okay, so what we get? dm1 dm2 is equal to, okay, to the numerator you are multiplying and dividing by Kb. So I write here Kc into concentration of M1, multiplying means writing here and dividing, writing like this. Okay, Kb divided by Kb, and write the remaining term as such, Kb into concentration of M2 into here Kc, right? Kc by Kc. Write the remaining term. Okay, Ka concentration of M1 plus Kb concentration of M2 and here Kc concentration of M1 plus Kd concentration of M2. Okay, this is what you get. Now what you do is here take this Kb denominator Kb that you take inside. So I write Kc and Kb together, concentration of M1. So what I am doing, I am writing 1 by Kb is there, that is taken inside, Ka by Kb into concentration of M1 plus Kb by Kb into concentration of, what is that, M2, right, M2 divided by Kb. I am writing Kc together. Okay, in this Kc taken inside. Okay, Kc by Kc concentration of M1 plus Kd by Kc into concentration of M2. Close the bracket. Now here, look here. Kb, Kb cancels, Kc, Kc cancels. So concentration of M1 by concentration of M2 is, open the bracket, Ka by Kb into concentration of M1 plus, here Kb, Kb cancels, only M2 is left, divided by Kc, Kc cancels, only M1 is left, plus Kd by Kc into concentration of M2. Okay, this is what you get. Okay, now what you need to do is consider the reactivity ratio. Okay, you need to consider the reactivity ratio R1 and R2. Okay, let me write here. Consider what? Reactivity ratio R1 and R2. Okay, R1 is given by Ka and Kb and R2 is given by Kd by Kc. Okay, now replacing here. So left hand side is this. So here you have M1 concentration, M2 concentration. Here R1 concentration of M1 plus concentration of M2 divided by concentration of M1 plus R2 concentration of M2. Okay, this is your final expression for the kinetics of copolymerization technique. Okay, this is a copolymerization equation. This is copolymerization equation. Okay, now this is the end of the derivation for the kinetics of copolymerization equation. If you have any doubt in this video, please let me know in the comment section. Okay, thank you for watching.